In some of the earlier videos, I was talking about PCA as a compression algorithm, where you may have, say, 1,000-dimensional data and compress it to a 100-dimensional feature vector, or have 3-dimensional data and compress it to a 2-dimensional representation. So if this is a compression algorithm, there should be a way to go back from this compressed representation back to an approximation of your original high-dimensional data. So given Zi, which may be 100-dimensional, how do you go back to your original representation Xi, which was maybe 1,000-dimensional? In this video, I'd like to describe how to do that. In the PCA algorithm, we may have an example like this. So maybe that's my example X1, and maybe that's my example X2. And what we do is we take these examples and we project them onto this one-dimensional surface, and then now we need to use only a row number, say Z1, to specify the location of these points after they've been projected onto this one-dimensional surface. So given a point like this, given a point Z1, how can we go back to this original two-dimensional space? And in particular, given a point Z, which is in R, can we map this back to some approximate representation X in R2 of whatever the original value of the data was? So whereas Z equals U reduced transpose X, if you want to go in the opposite direction, the equation for that is we're going to write X approx equals U reduce times Z. And again, just to check the dimensions, here U reduce is going to be an n by k dimensional vector, Z is going to be a k by 1 dimensional vector. So when you multiply these out, that's going to be n by 1, and so X approx is going to be an n-dimensional vector. And so the intent of PCA, that is if the square projection error is not too big, is that this X approx will be close to whatever was the original value of X that you had used to derive Z in the first place. To show a picture of what this looks like, this is what it looks like. What you get back out of this procedure are points that lie on the projection of that onto the green line. So to take our early example, if we started off with this value of x1 and we got this value of z1, if you plug z1 through this formula to get x1 approx, then this point here, that would be x1 approx, which is going to be in R2, and so and similarly, if you do the same procedure, this would be x2 approx, and you know, that's a pretty decent approximation to the original data. So that's how you go back from your low dimensional representation Z back to an uncompressed representation of the data. We get back an approximation to your original data X. And we also call this process reconstruction of the original data, where we think of trying to reconstruct the original value of X from the compressed representation. So, given an unlabeled dataset, you now know how to apply PCA and take your high dimensional features X and map it to this lower dimensional representation Z. And from this video, hopefully you now also know how to take these lower representations Z and map it back up to an approximation of your original high dimensional data. Now that you know how to implement and apply PCA, what I'd like to do next is talk about some of the mechanics of how to actually use PCA well. And in particular, in the next video, I'd like to talk about how to choose K, which is how to choose the dimension of this reduced representation vector Z.